The Tirukkural is a classic Tamil text from the 6th century consisting of proverbs in the form of couplets. The main aim of the author, Vallavar, was to write an instructive text focused on wisdom, justice, and ethics. In short, Vallavar undertook to spread goodness. I'm Elango. This talk is about the transpiler that Tim and I built called Kalei that shares the same lofty goal of spreading goodness. In the next 40 minutes, you'll be exposed to the ideas and techniques from program language transpilation, the inner workings of the Kalei transpiler, and reflect upon what's good in programming. The Kalei transpiler converts Clojure source code into Rust and Java source code. The problem we address is that most useful libraries only exist in a single language ecosystem. It's rare to see someone maintain the same library in multiple languages. We built Kalei to write code once and transpile it into other languages. Kalei is designed around 3 ideas: metadata on S expressions, rule-based data transformation, and splitting transformations into many small phases. My interest in transpilation is rooted in a desire to provide libraries that support the representation of human languages. I work at Google on internationalization, and I also serve as the Unicode Community Engagement Team Vice Chair. Our mission is to enable everyone in the world to use their own language and technology. I spend most of my time working on open source Unicode projects. The full breadth of human languages isn't so simple. Even the way that we write languages has lots of variation. Some are written with alphabets, some with ideographs, consonants only. Some are written left to right to left, or top down. And beyond that, grammar and vocabulary have even more variation. The computer technology stacks required to handle this are multi-layered themselves. International Components for Unicode, which is known as ICU, is a library of tools to make Unicode accessible in software. It can split text into sentences, words, and letters, even if the languages don't have spaces between words and sentences. It can determine the boundaries of text direction when you mix left to right and right to left, which happens a lot. It can sort text according to the specifics of the language. It can also format numbers, dates, times, etc. So if you want to make your software work globally, my advice is to always rely on the internationalization library rather than the programming language, because string and character manipulation for human-facing text needs special care. This is one of those things, like security, where you want to leave it to a proven solution and not just hope for the best naively. So get the libraries, the locale data, and more, turn to Unicode. The appeal of transpilation becomes apparent when you see the challenge of making this functionality available universally in technology. ICU is the leading industry standard internationalization library, and it's maintained in Java and C++. Other programming languages that need ICU functionality will either have wrappers around ICU, but they're incomplete, or built-in standard library functionality, but they're often incomplete and sometimes misleading. ICU is used in all of your computers and smartphones. However, that's not everywhere. We started a project somewhat recently called ICU for X to serve all of the places that ICU can't easily go. Its goals are consistent reproduction of algorithms across languages, targeting newer resource-constrained devices like wearables and Internet of Things, and optimization for performance. We had a couple of approaches for supporting other languages. One approach was to write code in Rust and compile it to a WebAssembly binary. And the main benefit of this is that we would get efficient performance. Another approach was to do transpilation. And the main benefit is the target language optimizations can be handled by native toolchains. But a transpilation tool for this use case didn't exist. So a teammate inspired me to try out this lofty idea of creating a transpiler. And that's when I started Kalei. If you're curious about the name, the word Kalei means art in Tamil. I figured if I'm going to do a transpiler, I got to do it in Clojure. I played with Clojure Tools Analyzer, and I was able to achieve basic functionality for assignments and basic types. Then I added support for functions, and I was pleasantly surprised and thought a transpiler is actually possible. And I started to use my 20% time to speed up my development. I added more features, and I made a demo number formatter. Meanwhile, ICU4X went in the direction of Rust and WebAssembly rather than transpilation, because ICU4X needs Rust to ensure optimal performance for resource-constrained devices. I persisted working on Kalei because I could see the potential. But over time, my progress slowed as the complexity built up. It was clear that it needed a simpler design. I talked with Tim, who is also building a Clojuresque transpiler using Meander. And my colleague Emmanuel Oga was interested in applying the NanoPass idea to the transpiler. So could Meander and NanoPass be combined to make transpilation more effective? We gave it a try, and it worked. Soon, we had recreated the features of the original project, and we were moving on to new and more challenging features. And we wondered, what else could we do? We got to thinking about potential use cases beyond ICU. We wanted to pursue use cases where there are no dependencies, so basically things that are largely based on algorithms, and where we could fill a void in the wider programming world that the Clojure community has long solved. Two use cases stood out to us: an SQL query builder and a data diff library. Using object relational mappers, or ORMs, for databases is difficult due to high complexity. SQL is often used to write queries, but it doesn't allow for code reuse. In Clojure, Honey SQL solves this problem by representing queries as data that can be composed and manipulated. But this solution hasn't made it out to Rust, Java, and other languages. The next use case we thought of was inspired by the Clojure unit testing library, Expectations. Programmers spend lots of time examining issues that their tests find. Expectations does a fantastic job of focusing your attention on the exact discrepancy. So in this example, you can see where and how the contents of the collection diverged. The second element should be 2, but the actual value had 3. This very special feature of expectations is actually based on the built-in function Clojure data diff. Given 2 pieces of data, it shows what's divergent and what's the same. This is effectively doing a set difference, but for data. When it came time to choose a language for the source code, we wanted to think about that from scratch. We didn't just want to plow into using Clojure because it's powerful, versatile, or we had warm, fuzzy feelings about it. And when you think about it, there are many programming languages out there to choose from. There are many good languages besides Clojure, and several that are more popular than Clojure. So the question of which source language is best is intertwined with implementation and representation. There's the language of the input source code, there's the language in which the transpilation logic is implemented, and there's the language or the format used to represent the programming constructs that we parse and transpile. Plain data and environment are 2 other important considerations. When Craig Andera hosted the Cognicast podcast, he often asked guests, what's the one feature you'd take from Clojure if you couldn't write in Clojure? And they almost always said persistent data structures. So let's talk about plain data first. In Clojure, everything interchanges with plain data. A small web application might have a database, a web page, and some data payloads, and some web-specific libraries. Each of the rows of your database will be represented as a map. When you interact with the libraries for HTML and JSON, you only use nested maps and vectors. Your libraries for UI layout or cloud service providers also give and take plain data. An adage of Lisp programming that we've all heard is code is data is code. And that's because S expressions are written in the data structures of the language. The real benefit for us from the flexibility of X expressions is that Clojure syntax doesn't change. That means that a library like Tools Analyzer, based on interpreting the syntax, will keep working for future code too. There are lots of ways to transform plain data in Clojure. The core library is a huge toolbox of composable functions. Medley and other libraries provide even more functions. Spectre is a lens library. It allows you to take a big nested piece of data and programmatically specify where and how to transform it. So it unwraps the data, applies your functions, and puts it back together. Meander is a term rewriting library. It enables declarative rules to transform data. For us, being able to apply the rule-based transformations onto very detailed AST data structures made a huge impact on what we could do, on our ability to reason about what we do, and ultimately on our productivity. To round out the power of the plain data ecosystem, you also have configurations. spec for an extensible version of optional typing, and property-based testing. Plain data connects all of the features of Clojure together. Let's look at how we represent the constructs. First off, let's start with a simple example of input source code. So here we have the form plus x1. Clojure forms like this are called symbolic expressions, or S expressions for short. An S expression can be represented by a tree of symbols, which we refer to as the abstract syntax tree, or AST. Some people simplistically state that Lisp code is the equivalent to the AST. In practice, there are more interesting aspects to the code than the symbols themselves. We care about data types and lexical scope bindings. For every node, we want to know the node type. For example, is it a function? Is it a variable? Is it a constant? A tree that captures meaning is useful and necessary. Clojure Tools Analyzer can take expressions and construct a detailed tree that captures the meaning that we need. This is very useful. However, it captures more information than we need, and that can make transforming and debugging unwieldy. How do we retain the useful information without cluttering up our S expressions? With metadata. On our original S expression, we can annotate X with the var provided to us by Analyzer. Equality isn't affected by metadata, so the new expression is equal to the old one. Metadata allows us to attach useful information to symbols and forms. And another way to think about this is that we're hiding extra information inside the S expressions. And this helped us simplify our representation in a way that works well with our transformation rules. When starting a project, we have to choose a programming language. And some people like to say, any program is expressible in any language, and use the right tool for the job. I don't find this advice specific enough to be helpful. Varlover said to always consider cost, means, time, place, and the action itself. When starting a project, your intention is to provide some specific benefit. So always consider the environment you operate in, how well your work will provide strategic value, and whether your tools are well suited for the environment. In different environments, you have different needs, constraints, and trade-offs. Your choices should be shaped by your circumstances. Programming project environments might have high stakes, frequent execution, changing requirements. An environment with changing requirements might value power and simplicity to help combat churn. For frequent execution, we value memory safety and performance. In a high-stakes environment, where the value is high and the risks are also high, it might be well worth the cost to employ formal methods that give you extra confidence. Languages are full of design decisions, each with their own trade-off. For example, simplicity and performance are always desirable, but sometimes they're at odds with each other. Design happens in the trade-offs that we make for specific requirements. When a language is well designed for the non-functional requirements of your environment, it's a good choice. Clojure is well designed for general purpose programming. It really maximizes simplicity and power. To illustrate the point, I want to tell you a story about when I worked at Nest. I joined because they were using Scala, which was close enough to Clojure for my liking. It's a functional programming language. It runs on the JVM. It has persistent data structures and a seek abstraction. I felt that everyone around me was more experienced and smarter than me, so I was insecure about how to write Scala. I decided that what I'd do was think about how I'd write the code in Clojure and then just type it out in Scala syntax. When I had my first code review, I was afraid that they would figure out what I was doing and then get mad at me. But instead they said, yeah, this looks like good Scala code because your function bodies have immutable bindings at the top and return statements at the end. The big project I worked on was creating a time series database out of thermostat log data. And I finished it on time despite having unforeseen major requirements added in the middle. The work I did wouldn't have been possible if I didn't go off and recreate some of Clojure's core library functions. Here's my implementation of merge with. Here's partition by. Meanwhile, everyone around me at Nest, at various points, eventually hit a wall with Scala where they gave up and they started building new projects using Java in anger. It was clear to me that thinking in Clojure and transcribing that into Scala allowed me to thrive in Scala. The Clojure way was the path to success. Kalei is the manifestation Kalei is the manifestation of our belief that we can transfer Clojure goodness to other languages. Next up, Tim will show us how to use Kalei and how it works.
Hello, my name's Tim. On weekdays, I work on a diagramming app called Hummy, and on weekends, I collaborate with Elango on Kalei. To use Kalei, you just start a normal Clojure project, put some code in your source directory, fire up a REPL, and start coding. Once we have something to transpile, we're going to add Kalei as a dependency. And so Kalei is going to go out and find all the source code, transpile it into Rust and Java, and then Cargo is going to compile our Rust code, and Gradle is going to compile our Java code. For Java, we need to pull in the bifurcan dependency. And bifurcan is a persistent data structures library by Zach Tellman. And for Rust, we need to pull in Rust persistent data structures and lazy static. Invoking make transpiles to our target language and then compiles to produce the binaries. The transpilation and compilation are both static, so any interactive development is limited purely to Clojure. So let's take a look at some of the generated code. For Rust, we create a module for each namespace. And we replace longs with I64s, we infix operators, and make it look like Rust. And for Java, we create classes, obviously, containing static methods. The compact data literal on the left transpiles to the huge thing on the right in Rust. This is, for us, it's just easier to adopt data-oriented programming when you actually have data literals, and without them, this sort of initialization is just verbose, tedious, and opaque. So I'm going to skip to just showing some example projects that actually transpile. We build an SQL builder that takes a map query, and then it formats that into a query string. And you can use this in Rust and Java to compose database queries. We made a data diff that just takes two arbitrary values, returns the difference between them. You can use it to improve debugging and test output in Rust and Java. And we also built a number parser formatter for different human number systems. So parse converts a human language string into a number, and format converts a number into a string based on a number system and a grouping strategy. These functions need to be efficient because we're going to execute them very often. And what's amazing about this formatter is that it's using mutability, it's using a string buffer, it's using types, and it's actually fast. And you can use it from Clojure, you can use it from Java, you can use it from Rust. With a disclaimer attached that you should really use ICU libraries for parsing and formatting instead. But for us, this was a big milestone. It showed, we can actually transpile performance-oriented code for low-level libraries that care about things like homogeneous types. And yeah, types. We do need to talk about types a little bit. So you can use Clojure type hints for primitives, obviously. For collections, we have a special type hint, a Kalei type. And types are always optional, but we encourage them. The transpiled code is going to be more idiomatic if you include types. It'll be more like the target language. So your types can be combined. We have an any type, which can be composed of anything. You can put your maps in your sets, in your vectors, whatever combination you like. Homogeneous types restrict what you can put into a collection, and you'd only want to do that for performance gains. All the collection types can nest. We provide type aliasing to give a name to a combination type, and type aliases just replacing the compiled code with what was aliased. And we also provide type propagation, which is just inferring what's the type of this thing. So in this example, we have Y. We know it's a long because X was a long, and we assigned it. We also provide mapped interrupt. So you would have noticed we used a string buffer, which is a Java class. And what we do is we map those string buffer methods to vector methods in Rust. Whereas in regular interrupt, you would have had to use reader conditionals to provide different implementations. So mapped interrupt replaces common interfaces instead. So you might be wondering, will my project transpile? Probably not. Kalei does not cover all of Clojure core, and there's several concessions that are necessary for transpilation. For instance, Kalei treats keywords as strings. There's no keyword type test, and HoneySQL relies on testing for keywords, and that's why we created a new library, a string-based SQL library. We also require sequences to be explicit, and that's why we made a new data diff library. We copied Clojure's data diff, but we had to make some adjustments to get it to transpile. So, Clojure has many features, and transpiling kind of feels like an impossible task, like we're trying to boil the ocean. But nevertheless, we can see there's a subset of Clojure programs that can be transpiled, and we believe that that subset is useful and that we can actually grow that subset with more work. So exactly how much of Clojure does transpile? We have loops, we have different styles, we have do times, do seek, while, they all compile. Macros we get for free, which is really cool. So an example of that is the while loop. Actually, macro expands out to a regular loop, so we don't have to do anything for that. And for the same reason, user macros work really great. You can require namespaces. We can define variables, assign data literals. We can manipulate data with assoc, update, conj, dissoc, and disjoin. And you can use atoms and local vars for mutation. We can define named functions and create anonymous functions. We can do map and reduce, but many of the other higher order functions you'd expect are missing. We have conditionals, if, or, cond, and case all work. You can use keywords as lookup functions if you want to, but collections cannot be used as lookup functions. So in summary, there's just enough Clojure to make small, useful libraries. We're going to switch gears a little bit and look at the actual implementation. And Kalei combines three core ideas, which are nanopass, term rewriting, and meta expressions. So nanopass is just a pipeline of small incremental transformations. Term rewriting is having a match and replace pattern for the transformation, and we use the meander library by Joel Holdbrooks for that. Meta expressions are just symbolic expressions annotated with metadata. So here's the pipeline, and I'm going to show you through each section in more detail, starting at the very top. So we have some Clojure code. It gets converted into an abstract syntax tree, and then meta expressions. And we'll look at an example where our function foo appends a bar to a vector. And so tools analyzer is going to read that code and give us the AST. And the AST is this huge map. Lots of useful information in it. We use meander to then transform that. So we annotate conj with the var conj. So the symbol conj gets annotated. And then we'll use meander rules, the match and replace, the question marks there indicate logic variables that connect the things that are in the match pattern with the things that are in the replace pattern that we want to change. So in my opinion, the transformations are very self-evident because the rule patterns imitate the exact shape of the data. Next, we perform a series of transformations that are common to all languages. And we start with constructs, our universal programming concepts, such as functions and variables. Constructs are explicit, disambiguated, and just common amongst all of the languages. So converting Clojure to constructs is a recursive process. We start with the namespace and iterate through all the top-level forms. We only support variables and functions as top-level forms. And all the constructs relate to each other recursively. So inner forms obviously nest other inner forms. Next, we transform operators so that they can be infixed in the output. In this example, nothing changes. And then we annotate the last expression of the function with a return statement. So now we're going to branch out into the Rust side of the pipeline. First, we convert all the constructs into meta expressions that represent Rust syntax specifically. So the syntax rule for Rust creates an R function and introduces an R block for the body. And then it recursively transforms the body as statements. Cast hints get transformed into explicit case statements. And then we go ahead and map var usages to their equivalent Rust methods. Condense removes all the unnecessary blocks, so double parentheses, operator groupings. And then stringify, finally, we produce the output, and the function string format here just creates a Rust function signature, and then it recursively stringifies the body of the function. And so each syntax construct in this world maps to a string function just like this one. So on the left here, you can see the set of universal programming constructs that we started with, and on the right are the Rust syntactic concepts that we produce. And you can see that through this incremental steps, we were able to move to this more complicated model. So overall, we really liked this pipeline. It worked well for us. We liked it because we could reason about things, and thus we knew where things belonged when we're adding code, and also we knew how to isolate things when we were testing it, and thus it just grew really gracefully. So I'm going to hand you back to Elango now to talk more about complexity.
Let's talk about complexity, and in particular, how complexity caught up and overwhelmed me when I didn't start with an appropriately simple design. In my original implementation, I only had one phase between the input and the output. The input and the output were both source code. So there was a lot of work that had to happen in that middle phase to simultaneously traverse the AST, transform it, and turn it into the final string. By the time I supported data literals, the code was unwieldy. The recursions were hard to reason about and debug, and functions grew to be hundreds of lines long. As proof of the rampant complexity, here's an eval buried deep in this function. And this function's full length was hundreds of lines long. This is how it felt. And this is what it was. I had multiple concerns intertwined with each other. The design work we did towards simplicity breathed new life into the project. The combination of analyzer, S-expressions, metadata, meander, and nanopass really did work. Varlover said, visualize actions with unclouded clarity. And in that spirit, let's examine where simplicity was brought to bear. Instead of one big transformation, nanopass is about composing more smaller phases. Transformations are incremental, easy to understand, and debuggable. We can validate each layer. Meta expressions as the representation are compact, they look familiar, and they work well with meander transform rules. Here's an example of how we annotated every tail position in Clojure as a return statement for the target language. Finding the tail position is a recursive algorithm. For a body of statements, only look at the last statement. For an if, then, else, recur into the then and else branches. And the base case is to add the annotation. For contrast, imagine if we were transforming the detailed map-based AST. It would start to look like the complex code I previously showed. These rules, on the other hand, are concise and obvious. Supporting data literals turned out to be tricky because it had to be recursive, and it had to handle the cardinality difference. The input is just one expression, whereas the output needs to be multiple statements, including building temporary variables and returning the constructed data collection. We solved this difficult problem by introducing a new grouping construct in our meta expressions and adding transformation rules using that construct. The solution was concise and easy to reason about. Simplifying the pipeline into simple, easy to understand rules enable powerful results. Clojure has many good things. Immutability, that is, a true value-based immutability, is one of those things. Persistent collections are more efficient versions of immutable collections. In order to represent all types of plain data, we need to be able to nest the collections, and so they need to be heterogeneous. Once we have heterogeneous persistent collections, we can start to offer better solutions that solve real problems. We can provide a way to reuse code in SQL queries when SQL itself doesn't provide that. We can think about unit test output as more as insights and less as a pile of messages. It's wild to me that programmers still write nested SQL queries that are dozens, sometimes even hundreds of lines long. And they turn themselves into human parsers of the output of their unit testing library. Imagine how much quick check style property-based testing could benefit languages that don't have it. And these things really do make a difference. Rich Hickey talked about this in his talk, Clojure Made Simple. When the first version of the React library for web page UIs came out, the Clojuresque wrapper that David Nolan wrote was 2 times faster than the original thing itself. And after spirited public discussion, the Facebook people behind React went off to write immutable.js to provide persistent data structures in JavaScript in order to create the second version of React. Transpilation isn't always straightforward because languages don't just differ in syntax, but also in semantics. So let's talk about the areas that made the most impact in our ability to transpile. Mutation was one of the biggest ways that affected transpiling Clojure to target languages. Kalei has the ability to support mutation semantics and immutability. And to support Clojure immutability, we need persistent data structures. We thought that it's more important to focus on the immutable way of programming because it provides simplicity, which matters so much for high-level general-purpose work. Fortunately, most languages have persistent data structure libraries. Mutable constructs already exist in the target languages. Another big discrepancy between the languages is the notion of memory ownership. Rust has formalized it as a language construct. It forces you to think about memory dependencies and memory allocation, whether it's on the heap or the call stack. We chose Rust as a target language, not because it is easy, but because it is hard. That's me being presidential. In particular, handling Rust would be a chance to test the boundaries of Kalei. For example, if the hardest part was supporting heterogeneous collections, even with the native library, we still needed to use Rust traits or interfaces to recreate an anytype, which is like how object is a global supertype in Java. As you know, I'm interested in human languages. Let me tell you a story about ginger. A few years ago, I was looking online for the etymology of the word ginger. The English word comes from the Old French, which comes from Latin, which comes from Greek, which comes from South Asia. Online sources said the South Asian origin was the Sanskrit word shrangaveram, which means horn body. I believe that was incorrect, and that ginger came from Tamil. Inji means ginger plant, and ver means root. Together, that's injiver. Doesn't that sound like ginger? We know that ginger was being used in the Indus Valley civilization at a time twice as old as the etymology of the word. Tamil originates from the Indus Valley civilization. And there are other words originating from Tamil in ancient times for South Asian crops that didn't exist in Europe, like rice and pepper. Where are these words really from? And when I checked recently, the same online sources have corrected their information that the origin is indeed from the language family of Tamil. It's an ongoing, complicated, and subjective situation. Similarly, when we think of programming languages, we shouldn't judge a language based on what the orthodoxy tells us, because that can change just as our collective knowledge evolves. The temptation is to differentiate languages for superficial reasons, such as how they look, which is the syntax. But that's not the biggest factor. Programming languages are more similar to each other than human languages because the domain of computers is much smaller and circumscribed. Where programming languages differ is in how their design is shaped around a particular model of programming. What's important is to evaluate how well that model of programming serves the strategic value in your particular environment. In conclusion, different languages exist for different purposes, and there's an opportunity to overcome the barriers among them and transfer Clojure goodness. We built a transpiler around 3 ideas: meta expressions, attaching metadata to S expressions, term rewriting, declarative rules to transform data, and nanopaths, a pipeline that composes many small phases. Designing for simplicity enabled us to achieve things that exceeded our expectations. Vardovur said to be unremitting in doing good, and that message resonates with me. It motivates me to share what I've found good in my domain. Clojure is well designed for general purpose programming, so let's keep sharing Clojure with the wider community. I've really enjoyed soaking up the inspiration here at the Conj these past couple days, hearing the new ideas and seeing all the amazing things that people are building. It's clear to me that everyone here values goodness, and I encourage you to share that widely.